Hello everybody, so welcome to this third video on Markov chain Monte Carlo. Today we're going to speak about chapter 3, ergodicity of dynamical systems and law of large number. So the important result of this course is that when you have a Markov chain with a unique invariant probability measure, then the associated dynamical system is ergodic, and as a consequence you can have a law of large number for your Markov chain. So let's see that in more detail. So we're going first to minimize, and then we're going to start with some refresher about dynamical systems. So let's look at the first paragraph, so dynamical system. What do we call a dynamical system? So for this section we are going to forget all about Markov chain because we just focus on dynamical system. So a dynamical system is some quadruplet constituted of omega, f, p and t. So omega fp is a probability space. You have omega here, which is a space, a sigma field f on the space omega, and some probability which is defined on the sigma field f. So you have a probability space, and you add the last component, you add a function which is actually a measurable mapping from omega to omega, such that you have this property. The probability p is equal to the probability p circ composed with the function t minus 1. Okay, so it means that p of a is equal to p of t minus 1 of a. Okay, we're going to see later what it means exactly. One nice, one important set for dynamical systems is the invariant sets. How it is defined? So A is an invariant set if the indicator of A is the same as the indicator of A of t. So you have this property which is stated here, and this property tells you that A is an invariant set, and what you call as I is the set of the invariant sets. Okay, and I as a set of sets is actually a sigma field. So if you have all the space which is inside, and you have some stability under complementation. If A is an invariant set, the complement of A is also an invariant set, and you also have some stability under the intersection. So if all the AI are in invariance, then the intersection of all the AI are invariant also. Okay, so this is the first result, and we say that a dynamical system is ergodic if any invariant set has a probability which is either 0 or 1. Okay, any invariant set has a probability which is either 0 or 1. And the important thing that we're going to use here is that when you have an ergodic dynamical system, then for all h in L1, you have that the limit of 1 over n, the sum from k from 0 to n minus 1 of h of t to the power k. T to the power k means t composed k times. So this limit exists, and the value of this limit is expectation of h. Okay, this is an almost sure result, meaning that if you look at this event, the fact that the limit exists and is equal to expectation of h, and this event has a probability which is equal to 1. Okay, so this is just some important facts about dynamical systems, and actually we are going to go back to our problem. So we have a Markov chain, we have some Markov kernel, and we want to link in some sense our Markov chain to some dynamical systems that we're going to define, and then we are going to use results on dynamical systems to obtain other results on Markov chains. So, okay, so when you have a Markov chain, you can define the shift operator, so just shift by one time index. So it S is such that S of W0, W1 and so on, if you apply S, then you get some infinite trajectory, which is W1, W2 and so on. So you have just shifted the index by 1. Okay, so when you look at your Markov kernel P with some invariant probability measure that I note pi, then you will consider the space of trajectories, the sigma field associated to the infinite trajectories, some laws that we define on this canonical space, and this is a law starting from pi. So you have pi as the distribution of x0, and then you will define a law which will concern not only x0 but x1 and so on the whole trajectory. It's p indexed by pi, and then you have this function which is S, which is the shift operator. And actually this is a dynamical system, and the only thing that we have to prove is that to obtain a dynamical system, I recall that a dynamical system is defined essentially by this property, okay, which may seem a bit abstract here, but if you look at your Markov chain, it will be clear now, because what we want to show is that we want to show this thing, okay? We want to show this thing where S is the shift operator. So to see this, recall that this is the same as this, and actually when you want to look at the probability of x0 infinity belongs to S minus 1 of A, it means, because S is the shift operator, it just means this. And this is finally a consequence of the fact that you have under the probability P pi, you have that xt as a time series is a strongly stationary sequence, meaning that if you have x0 to infinity, if you shift everybody by 1, and if you look at x1, x infinity, it has exactly the same law. Okay, so this is completely easy consequence of the fact that you have a strong stationary sequence under p pi, and then we are done. We have a dynamical system. Now there is some approximation lemma that will be technical, so you might, if you want, try to solve it for people who are interested in this, but otherwise it's just a technical lemma. The proof is not that important. It uses the monotone class theorem, but the consequence is interesting. It's a way to approximate a set which is on the whole trajectory. So you have, it's on the whole trajectory. So so it may be a bit complicated, okay? And actually it can be approximated by a set which is on Fk, okay? Fk is just the sigma phi generated from x0 to xk. So in the sense that for any delta there is a b in Fk, such that if you take the difference between the two indicators and you take the absolute value and the expectation under pi, then this is smaller than this arbitrary delta, okay? So any set on the whole trajectory may be approximated by a set on a finite number, concerning a finite number of x. So that's very interesting. And this will be used to prove this famous theorem 3.7. We're not going to prove it in this video. I encourage you to do the proof because it's very interesting. It's just 1 page long. And I will do another video just to prove the theorem 3.7. But let's look at the statement here in this video. So in the statement is very simple. So you have here Markov kernel P, and you assume that there is a unique invariant probability measure. With this assumption, then the associated dynamical system is actually ergodic. Okay? So that's very, very interesting, because since it is ergodic, you can apply the Birkhoff theorem, and you get that under p pi, so we are here, under p pi, so it's this result which is important, under p pi, then you have the limit of this quantity is equal to expectation of h. Why do we have this quantity? Because h of this is exactly this, okay? Now if you take a particular case where h of x0 infinity is just a function of x0, then h of xk infinity, it is just f of xk. So if you replace here this by f of xk, then you will get this conversion. So you have a law of large number, which is nice, but pay attention that here it is under p pi. Why it is under p pi? Because it is only when you take the invariant measure as the initial distribution that you can have a dynamical system. Here we have a dynamical system under p pi, okay? So we can use it only with the starting distribution, which is pi, so it's not very nice. But we have a good result, which is here, which is that as soon as you have this under p pi, then you will get this under px for not all x, but pi almost all x in x. And actually it's like an exercise that we have done last time, is that this event can be said we call it A, okay? And p pi, the fact that p pi almost surely A holds means that p pi of A is 1, or p pi of A complement is 0, so you have this. And recall that we have seen a link between p of starting from pi and p starting from x. And this link is given here. Now if you assume that something is equal to 0 here, it means that you integrate with respect to pi something which we know it is positive. So if we know that this integral is equal to 0, so it means that this quantity is 0 for pi almost all x. Okay, for pi almost all x belonging to x. So this is expressed in corollary 3.10. And for Metropolis Hastings, you have an even stronger result, which is nice, which tells you that you can have, because here this is a good result, but it's not for all x. Now we are going to have a result which is even stronger for the Markov kernel associated to a Metropolis Hastings, that this limit holds for any initial distribution nu, especially for any x also. When you start from any point, you have the law of large number. So you can look at the proof, which is quite short, and it's very interesting, and he has some nice practical applications. It is the fact that when you start your Metropolis Hastings algorithm, you can take any point. You know that at least starting from any point, you can have a law of large number. And the last result of this course is when you want the same result as for the Metropolis Hastings algorithm, that is a starting point which is any measure nu, but you don't want to have the assumptions that you are under the Metropolis Hastings. Okay? Here is a very nice result, but you are on the assumption that you consider a Markov chain generated by the Metropolis Hastings algorithm. So when you are not under this assumption, but if you can show that for any bounded function h and any measure nu, you have the following limit. So it is nu p Pn of h converges to P of h. So it is nu Pn. This is the distribution. Recall that Xn has a distribution nu Pn. It means that if you look at the integral with respect to this distribution of the function h, it means that you consider the h of xn. If this converges to pi of h, then you can show that you can have this limit. So this is very interesting for you, because you can have the same result as a Metropolis Hastings, but not only with this kernel, but for any kernel, such that you are able to prove 3.7, this condition 3.7. Okay? So we won't make the proof of this, but it is written here, so it's not very long. If you want to have the proof, you can look at this. So maybe during the course we are going to show this. Okay, thank you for your attention. So maybe before leaving, just to make a recall of what we have done. So now, after studying this chapter, you have understood that you can use the law of large number for any Metropolis Hastings algorithm starting from anywhere. So that's very, very nice. If you want to check a law of large number, you can first check if your Markov chain has a unique invariant probability measure, in which case you can have a law of large number starting from initial distribution, which is pi. Then you have also some variants of that. You can have this result with starting from any point x for pi almost all x in the space. And you can have also a very deep understanding of this result if you look at the proof, which is pretty hard but very beautiful. And you have also, I didn't say here, but you have also some other results, especially the last one can be interesting. You can have also a law of large numbers starting from any point as soon as you have a unique invariant probability measure and this additive condition, 3.7, okay? So thanks for your attention and see you next time.